In the first three lectures in this unit, we're going to be talking about spectral types, which is what you are working on in the lab activity that you're doing in class using the data from the Sloan Digital Sky Survey. And in the lab, you don't always see the details about what we're trying to get you to learn from it. So that's what I'm going to be talking about, is some of the explanations behind why you're seeing what you're seeing in the lab. So in this lecture, I'm going to talk about what's called line strength. In the lab, when you have been looking at the spectra of different stars, like these are two of the ones taken from the lab, we certainly see absorption lines. There's some very long ones here, there's some shorter ones here. And you've been asked to particularly pay attention to the H-alpha transition, which is what is the transition from level 2 to level 3. That's n equals 2 to n equals 3, as it happens. That's this one here and this one here. That's a very useful one because it comes right in the visible part of the spectrum. It's at about 670 nanometers or so, and it's very visible. It's definitely red, and you even saw it in the lab we did earlier this week. And then you can also look at the H beta one, which represents the 2 to 4 transition. But when you look at these, you'll notice that you can compare these and see that on this spectrum, the lines are a lot deeper than they are on here. They go down a lot farther. And there's also perhaps a difference in the width of them. It's kind of hard to tell at this scale, but you might make the case that, for instance, this one is wider than that one. So there's a difference in the depth and in the width of the absorption lines that you see in a spectrum. And this comes from what we call line strength. Line strength is just a combination of the width and depth of a line. Usually it's going to be absorption lines, but there are places in astronomy where it's an emission line when you're looking at the spectrum in a graph form. You can't really see the line strength too well when it's in that sort of rainbow form, but in this form we can definitely see the width and the depth of the line. If I want to estimate the line strength, and you're doing that in your lab, what you do is you start by sort of estimating where that continuous background would have been. So I can kind of imagine drawing a line from here to here. I would say that that's sort of where the background went. And then I can imagine filling in all of this area that got absorbed. Obviously, I'm not doing this terribly accurately right now. Coloring on my computer is not my greatest strength. I can fill in this area, and if I wanted to figure out what this area was, if I wanted to actually calculate the area, for instance, by adding up all of the little boxes, so 1, 2, 3, 4, 5, 6, and so on, you have to kind of estimate on some of them because they're not complete boxes, but you add up the area, and that will give you an estimate of how wide it is and how deep it is. That will tell you how strong the line is. The greater the area is, the stronger the line. Greater area goes with stronger lines. So you're going to see some that you do in the lab that are very strong because they have a lot of depth and width, and others that are not so strong. They have less depth and width. And that's going to be a way that we can use to classify stars. We can classify stars based on how strong their absorption lines are. And so in the next two lectures, you'll be seeing how we actually perform that classification.